All right, welcome back. We are continuing our discussion of entropy. We've determined that entropy is the sole predictor of spontaneity. We've talked a lot about how to calculate and estimate entropy, but mostly we've figured out how to calculate the entropy change of the surroundings, being minus delta H over T. But we haven't talked too much about the systems yet. And so let's start talking about the systems. How do we calculate entropy changes in systems quantitatively? Right? We qualitatively did it. We predicted, oh, this one's got greater entropy than that. It's got to have a positive or negative entropy change. But if we really want to know spontaneity, right, we need to know quantitatively that our entropy change of the universe is greater than 0. So we need to quantify this stuff. So remember, we talked about where S comes from. It comes from this guy, S equals K times the natural log of W. That equation right there is what tells us how to calculate entropy. It's an absolute number. We talked in our last video about how we had our enthalpies of formation that we looked up in tables because we didn't know how to measure enthalpy directly. In fact, there's no way to measure enthalpy directly. We can only measure the movement of heat. We can't measure absolute heat, but entropy we can measure absolutely. So it turns out that there's another necessary component to this equation existing. Is what happens when W is equal to 1. We get S equals K times the natural log of 1. The natural log of 1 is 0. And so we get 0 joules per mole Kelvin. So when there's only one way of arranging things, we actually have an entropy of 0. Now, it turns out that's impossible. It turns out that's absolutely impossible. Why? Well, in order for there to only be one way of arranging things, you actually literally have to have an infinite-sized perfect crystal. Right? It has to be a perfect crystal because there has to be no blemishes in it, right? Carbon, think about graphite, or think about diamond. No blemishes in diamond whatsoever. Everybody's in this tetrahedral arrangement. But as soon as you get to an edge, right, you have a choice in how to make that edge. Is that edge going to be slightly pointy? Is it going to be not pointy? Or anything like that on a molecular scale. And all of a sudden, you've got choices. And choices mean that W is not just 1. And so you can never have an edge to your crystal. It's got to be perfect. And so it's an infinitely large, perfect crystal with no motion whatsoever, because it turns out that motion is even different ways of arranging it. If I'm moving, I can be over here and I can be over here, and that's all of a sudden two different ways of arranging things. And so it's got to have no motion, a perfect crystal, infinite size, in order for W to be equal to 1. And it turns out that's actually such an important concept. And it seems a little strange, but it's such an important concept. That's actually the third law of thermodynamics. The third law of thermodynamics defines what 0 entropy is. Because if it didn't, then it turns out we can't calculate any of this other stuff. We're not going to get into the details of all of that, but let me go ahead and give you the third law of thermodynamics. The third law of thermodynamics says this. The entropy of a perfect crystal, right? And a perfect crystal is one that's everybody's perfectly arranged and it's infinitely large. At 0 Kelvin, and remember 0 Kelvin, Kelvin temperature is a measure of energy. And so at 0 Kelvin, there is 0 energy, which means there's no motion whatsoever, is 0. Right? That's it. That's really neat, right? That there's actually a third law of thermodynamics that says this thing that doesn't exist, it can't possibly exist, a perfect crystal, has 0 entropy at 0 Kelvin. Without that base definition, all those other entropies wouldn't make any sense. Okay? So this is the third law of thermodynamics. The entropy of a perfect crystal at 0 Kelvin is 0. But we can't actually ever get to 0 Kelvin. It's not possible. We can get down very close. We've gotten down to microkelvins or even nanokelvins, I believe. But we can't actually get down to 0 Kelvin. And the entropy of that perfect crystal is 0, even though we can never make that crystal. Okay. So when you look up in the tables, like I said, what you're always going to find is you're going to find S naught. You're not going to find S formation. You're not going to find delta S of formation. Just S naught, because we can actually calculate absolute entropies thanks to that third law of thermodynamics sitting right up there. And so if we wanted to calculate entropies of reactions, it turns out they work exactly the same way as we do when you calculate enthalpies of reactions. So remember, when you're trying to calculate the reaction enthalpy at standard conditions, that's what that little circle means. At standard conditions, that's just going to be the sum of the enthalpy formation of your products minus the sum of the formation enthalpies of your reactants all multiplied by their stoichiometric coefficients, right? So if you had 3 of something, you'd take 3 times the enthalpy of formation. So that's just products minus reactants. It turns out that entropy is exactly the same. So you said, I said at the beginning of this that I take many, many, many hours of your life to describe all this background things. And in the end, the calculations would be relatively simple. And calculating entropy from a table of entropies is actually really simple. It is exactly what you did for enthalpy. There's no difference whatsoever. You just use entropies instead of enthalpies, and it's products minus reactants. So let's do an example. Let's do the reaction 2 nickels plus 3 O2s goes to 2 SO2s and 2 nickel oxides. So we've got something that looks a little like that. And it's hopefully a balanced reaction. And what we're going to do is we're just going to go to a table, right? On a test or quiz, you'll always have access to those tables that I give to you. And we're going to look up those entropies, those standard entropies, again, not a formation. And remember, they're not going to be 0. We can have enthalpies of formation. If we looked up the enthalpy of formation of nickel solid, that's nickel in its standard states. That's what it is at 25 degrees Celsius and 1 atmosphere of pressure. And so it would actually be 0 if we were looking up the enthalpy of formation. But entropies are never going to be 0 unless it's a perfect crystal at 0 Kelvin, which is not at standard conditions, is it? So all of these are going to be in units of joules per mole Kelvin. And we can just look those up. This is 53, and that's for each nickel. Right? I'm not doing the stoichiometric coefficients yet. This is 20. Is that right? 20 joules. I'm sorry, 205. There we go. 205. Like 20 doesn't sound right. 205, 248, and 38. And you'll notice, right, our solids, relatively small entropies, our gases, relatively large entropies, which is what we expect. Gases have a lot more entropy than solids or liquids do. So how do we figure out the standard entropy change of the reaction? Is products minus reactants times their stoichiometric coefficients. 2 times 248 joules per mole Kelvin plus 2 times 38 joules per mole Kelvin minus 2 times 53 joules per mole Kelvin plus 3 times 205 joules per mole Kelvin. Right, we got to make sure to put the parentheses around those last set of numbers, so you're subtracting both of them. That's really important. And if you go ahead and calculate that, you're going to get a minus 149 joules per mole Kelvin. Now, we could have predicted the sign of this one, saying, hey, it's going to be a negative entropy change by the fact that we went from 3 moles of gas on the left to 2 moles of gas on the right. We could predict a negative entropy change, but now we actually calculate it, and we know this actual value. Now remember, when we're talking about reactions, that's usually the system, and so you'll also see people write this, and you'll also see people write that. And all 3 of those mean the same thing. The delta S of the reaction is usually my system, so I can write it as delta S naught, and I can write it as delta system S naught. All 3 of those are equivalent ways of writing it when we're talking about a reaction as our system. All right, so we get a negative 149. Again, we still have to figure out what to do with that, and why is that number useful? Because if you remember, the predictor of spontaneity is not what's my delta S of the system. Right? We just calculated quantified delta S of the system. the predictor of spontaneity is what is the delta S of the universe. So we're still not there. We're still not to something useful that can actually predict whether a reaction is going to happen or the reaction is not going to happen. All this time, how can we still be nowhere? Because we're a lot closer than we used to be. Okay, let's remind ourselves that the universe is my system plus my surroundings. Now you notice I don't have this little circles there because this is universally true. This is universally true. It's true at standard conditions. It's true at non-standard conditions. It's true anytime in the entire universe. It's the second law of thermodynamics. It says this has to be greater than 0 in order for a process to be spontaneous. So I could put these little guys here, and that would also be true because it's true anytime whether or not I have those circles there. Right? The circles are always a special case. The lack of circles is any case. Okay, so I've got this one, delta S is greater than 0. But what have I figured out? Well, I figured out a few things in the last several videos. I can calculate my system entropy by using tables, right? That's very specific to standard states, but we'll see that we can change our style to standard states later. But I also figured out an equation for delta S of the surroundings is delta H over T. And I'm actually going to go ahead and use system here. Delta H over T of my system. So cool. Now what I'm going to do is I'm just going to multiply by T on both sides, and you'll see why later. So I've got T times the delta universe of the system is delta S of the system times T minus delta H of the system. So I've got this relationship here. So temperature is always greater than 0, right? So all I have to do is make sure that this side is greater than 0, and then the delta S of the universe is always going to be greater than 0. But how do we do that? Well, excuse me. Let me go ahead and do something that's not going to make much sense to people who haven't been studying this for a really, really long time. And I'm going to go do two things. I'm going to put a negative on both sides here. So I'm going to negate this whole thing. Right, and now I have negative T delta S of the universe is minus delta S of the system times temperature plus the delta H of the system. And then rearrange this. It's going to be delta H minus T delta S. I'm going to take off my little subscripts now, but it means the same thing, right? Delta H and delta H of the system means the same. Delta S and delta S of the system means the same thing, because without the subscript, we assume we're talking about the system. Now, I'm going to do something that doesn't sound like it makes a lot of sense, but I'm going to define a new thermodynamic quantity. Right, can you just do that? The answer is yes. They do it all the time. Now, why are we going to define this one? Not because it's obvious and, oh, duh, of course we're going to define this thing, but because a lot of really smart people worked on this for many years of their life and figured out that this is actually a really useful definition that gives us a tool for predicting spontaneity. Okay? And we're going to define this thing called G, and it's going to be defined as, if you remember from math, you might have learned once that 3 bars is the definition. It's going to be defined as H minus TS, right? And if we look at that this way, we can say delta H D equals delta H minus T delta S, assuming a constant T. Now we're going to take away the constant T assumption later, but right, it turns out in order to do this step, we are assuming a constant temperature. And so we have delta G equals delta H minus T delta S. And so look, I've got delta H minus T delta S. So this thing on my left must be equal to this. So I've now got that delta G is minus T times the entropy change of the universe. And you remember the entropy change of the universe is my sole predictor of spontaneity. Right? This must be positive in order for something to be spontaneous. Temperature is always positive, And so my delta G is going to be negative for all spontaneous systems. So if something's going to happen, there's this thing that we just defined called delta G, a change in what's called the Gibbs Free Energy. G is the Gibbs Free Energy. Let me write that up there. And it's not free as in, you know, here, have a free hamburger on us, right? It's free as in available, right? It can be used to do things, right? So it actually, this thing tells us how much energy do we have available of all the energy there is, because it turns out enthalpy has energy in it. Entropy actually has energy in it, right? It's in joules of joules per mole Kelvin. Right? Of all that available energy, how much can we actually do something useful with? That's what it means by free. It's the available energy. But we know that delta G is going to be negative for all spontaneous systems. And we also know it's going to be positive for non-spontaneous. Because the only way for it to be positive, since temperature is always positive, the only way for Gibbs free energy to be positive is if my entropy change of the universe is negative. And right, negative there times this negative would give me a positive. And so it turns out if we have a positive Gibbs free energy, we know that this reaction is not going to happen all on its own. It's not going to happen without outside intervention. It's not going to be a spontaneous process. All right. So that's what we end up with. Now, why is that useful? Well, because we now have this predictor that we know we can calculate, and if it's negative, it's a spontaneous process. But how do we calculate it? We calculate it really easily. We calculate it using the enthalpy change of the system. We can look that up in tables for chemical reactions. And the entropy change of the reaction. We can look that up in tables for chemical reactions. And the temperature, right? That's going to be given to us in general. Okay? And so we now have a way of calculating, essentially, the entropy change of the universe by looking only at our system, which is crazy. Right? Really, Alpha Centauri is part of the universe. And so we're actually looking at the entire universe and how its entropy changes just by looking at what our system does. What kind of heat is our system releasing? What kind of entropy change is happening in our system? And we are able to predict completely the spontaneity of the reaction, which is the entropy change of the universe. Wow. That is a pretty amazing thing, to go from universe to system and have it work. And it does, and it works really, really well, which is why we have this thing called the Gibbs free energy, is because it works perfectly to predict spontaneity. All right. Now, just so you're aware, like I said, this is constant temperature. It's also constant pressure. Why? Because in order to get that relationship of Q is equal to delta H, that was at a constant pressure. Now, oftentimes we'll violate the constant temperature, not so much the constant pressure requirement, to say, hey, look, yes, this was derived at a constant temperature, but it turns out that it's pretty good if you're not changing temperature that much. So if you're changing temperature by 10 degrees, 50 degrees, this equation works pretty well. It's not going to be perfect anymore, but it works pretty well. But if you're trying to change temperature by thousands of degrees, this no longer works because we made some assumptions in deriving it. So we will actually find out that we should only use this at a given temperature when we calculated delta H and delta S at that temperature. Notice I don't have the little standard signs on them. This equation is generally true, but the delta H, if you're trying to do it at 500 Kelvin, had better been calculated at 500 Kelvin. The delta S had better been calculated at 500 Kelvin, and then your delta G is for 500 Kelvin. We will violate that. We will go ahead and use delta H's at standard conditions with the little circles on them, and then say, oh, the temperature is 300 Kelvin instead of our 298 Kelvin, 320 Kelvin or whatever, instead of our 298 Kelvin. But that's pretty good, and it works well enough that for our purposes and for most purposes, it's a pretty good assumption and a pretty fair assumption. But I just wanted to be clear about that, as clear as thermodynamics can ever be. All right, so we've got this way of calculating spontaneity, which is really cool. So let's go ahead and see how well this works. We're going to calculate delta G for this very simple reaction. H2O gas goes to H2O liquid. We're going to use delta G equals delta H minus T delta S. And we're going to look these things up, and we're going to find the following, that delta H naught for this reaction is 6.03 kilojoules per mole. It is it is exothermic, and so we should have a negative there. Our delta H is minus 6.03 kilojoules per mole because we're going from a gas with lots of energy to a liquid with much less energy. That energy's got to go somewhere, so my enthalpy change has to be negative. My delta S naught is going to be 22.1 joules per mole Kelvin. And let's go ahead and calculate this at standard conditions. All right, well, let's go ahead and just violate our temperature thing just to begin with. So we're going to look at this first at positive 10 degrees Celsius. At positive 10 degrees Celsius, it turns out delta H and delta S, we can use those standard state ones, and it works out pretty well. We're going to calculate delta G equals delta H minus T delta S, and we're going to say that that is minus 6.03 kilojoules per mole minus temperature, right? 10 degrees Celsius is going to be 283 Kelvin. Always have to be in Kelvin, right? Because our units down here are in Kelvin, times 22.1 joules per mole Kelvin. Now, a very common mistake is to plug that in your calculator and go from there, but you'll have to notice something that's really important. Here I've got kilojoules, here I've got joules. Because they are generally measured in slightly different units, we do have to convert between them. Since we're calculating a delta G here, that is generally reported in kilojoules, so I'm going to go ahead and convert my joules to kilojoules rather than the other way. So I'm going to actually just add this step on here, that there is 1 kilojoule for every 1,000 joules in order to plug that into my calculator. So this one's pretty simple. You're going to go ahead and you're going to take your negative 6.03 and you're going to subtract off 283 times 22.1. Excuse me. And you're going to get oh, there we go. I was confusing myself because I'm trying to think ahead. This is supposed to be solid, which makes this positive. Sorry about that. Okay, the solid going to a liquid, I'm melting, okay? I'm melting, so it's an endothermic process, which means this is a positive 6.03 down here. Oh, that makes my life much easier because I'm thinking to myself, why isn't this working out? It's because I wrote down the wrong thing. It happens. We all do it. Okay, so at positive 10 degrees Celsius, this is minus 220 joules per mole. I'm sorry. This is going to be, let's go ahead and type that in. It's going to be divided by 1,000. I forgot to put the 1,000 in my own calculator. I had it there for you. And this is going to be minus 0.224 kilojoules per mole. Okay, so what does it mean for it to be negative? This means it is spontaneous. So what did we just say? We just said, hey, look, at 10 degrees Celsius, this reaction of solid going to liquid is spontaneous and will happen. But let's check it out at a different temperature. Let's check it out at minus 10 degrees Celsius. What's going to happen at minus 10 degrees Celsius? Well, everything else is going to be the same. I'm going to get my delta G is equal to positive 6.03 kilojoules per mole minus, the only thing that's going to be different here is my temperature. Instead of be 283, it's going to be 263 Kelvin times 22.1 joules per mole Kelvin times 1 kilojoule over 1,000 joules. And you get something like that. And when I do that, I'm going to get a positive 0.224 kilojoules per mole. And so I'm saying at negative 10 degrees Celsius, this reaction is not spontaneous. So the reaction of going from a solid to a liquid is not spontaneous at positive 10 or negative 10 degrees Celsius, but is spontaneous at positive 10 degrees Celsius. And I'm going to do one more thing that's very magical here. What happens at 0 degrees Celsius? At 0 degrees Celsius, I'm not going to do the math for you, right? It's going to be 273 Kelvin. I end up with that delta G equals 0 kilojoules per mole. And that's an interesting one. What does it mean to be 0? We'll figure that out in just a moment. But let's look back here. What did I just say? I said at positive 10 degrees Celsius, this reaction is spontaneous, going from a solid to a liquid. At negative 10 degrees Celsius, this reaction is not spontaneous. And so all this stuff that we've done for the past several videos, probably several hours of your life by the time you looked through this, took notes, did all the things you did, all to prove to you, quantifiably and without a doubt, that when it's warm, ice melts. And when it's cold, ice doesn't melt. You're never going to get that time back. Sorry. But we know now that it's true. We can prove it quantifiably, which is kind of cool. Okay? Right? We always start with the easy things. We start with the things that we can understand so that later on when we do things we don't understand, we have some like, hey, this works. And we know it works even in a situation where it doesn't. All right. Here's another couple things to talk about. This positive delta G means it's not spontaneous the way it's written. So it's not spontaneous where we go from a solid to a liquid. But what it does mean is it's spontaneous in the reverse direction. A positive delta G doesn't just mean it's not going to happen in any way, shape, or form. It just means it's not going to happen the way you wrote it. But it also does mean that it will happen in the opposite way that you wrote it. So at minus 10 degrees Celsius, the backwards reaction will happen, which is a liquid will go to a solid. So we just showed that, yes, at cold temperature, water freezes. What about this 0 degrees Celsius? The 0 degrees Celsius and saying delta G is 0, what does that mean? Well, what happens to solid and liquid at 0 degrees Celsius? Is nothing, right? They're actually at equilibrium. And so this tells us a little bit about equilibrium. Ooh, we're relating thermodynamics back to equilibrium. That's really cool. Energy and heat is actually predicting equilibrium, which we said before was just these kind of quantities, this power over that power. We were able to calculate it without thinking anything about energy and heat. But energy and heat is the predictor of equilibrium. Really, really cool. All right, one for you. At what temperatures is the following reaction spontaneous? Bromine liquid goes to bromine gas. I gave you some delta H values. I gave you some delta S values. And you're trying to determine at what temperatures, possibly, is the following reaction spontaneous, right? So we have to determine what determines spontaneity, how do we calculate it, and how do we relate that to temperature. So go. What did you come up with? Well, what I did is I said, hey, look, my predictor of spontaneity is delta G. And I know that it's going to be delta H minus T delta S, right? And so I know that at 0 delta G, we're talking about equilibrium. And so a cheater way, one way would just be to plug in numbers and start plugging in those temperatures and see where your delta G is negative. Absolutely fine, perfectly great for this problem. If that's how you did it, kudos to you, you're doing it fine. I'm going to cheat a little bit, And I'm going to say, hey, look, I know this reaction's at equilibrium when delta G is equal to 0. And I know if I'm on the right side of equilibrium that this will all work out. So I get the delta H is T delta S, if I just move that over by adding it to both sides. And I get the temperature is going to be delta H over delta S. And if I do delta H over delta S, I get 31,000 joules per mole divided by 93.0 joules per mole Kelvin. Notice how I converted my kilojoules to joules there. I just did it in my head for this problem. And if you divide those two, well, I didn't do it in my head. I did a calculator because I'm not that good at math. All right, if you calculate that, you get the T equals 333 Kelvin. Okay, now that's when it's equilibrium, which means below that temperature it's going to go one way. Above that temperature, it's going to go one way, the other way. And so my break-off temperature looks like it's going to be somewhere around there. So is it going to be at 300 Kelvin, or is it going to be at 400, 500, and 600 Kelvin? Well, if you look at my possible problems there, I can actually end now because there is no choice for just number 1, but there is a choice for numbers 2, 3, and 4. So I know it's going to be these ones just because the problem statement tells me so. But let's say I didn't have those multiple choice things. I was just trying to figure that out. What can I do back here? Well, I can go back and I can look at the signs of everything. Here, my delta H is positive. My delta S is also positive. So at very, very, very low temperatures, like let's say 0, we can't actually get to 0, but we can pretend we can, my delta G is going to be positive, right? Because my T term is going to go to 0. So my delta H is going to be positive. So at very low temperatures, I have a positive delta G, and that's going to be non-spontaneous. What about at very, very high temperatures, like say 1,000,000 Kelvin? Right? At 1,000,000 Kelvin, I've got a positive number minus a very, very, very large temperature times the positive number. That's going to give me a negative number. Right? And so at very large temperatures, I get a negative number. At very small temperatures, I get a positive number, which means at large temperatures, I'm spontaneous. At small temperatures, I'm not. And so that's how I can come up also with the 400, 500, 600. Again, you can just plug those in as well. You can plug in 400, plug in 500, plug in 600, and find that delta G is negative in all of those circumstances. All right, and in general, we can actually just look at the signs of delta H and delta S to tell us something about how the system is going to respond. So if we look at delta H, delta S, and we look at the spontaneity, when delta H is negative, so we have an exothermic reaction, delta S is positive, so we have something where the system increases in entropy, the system is also releasing heat, our spontaneity is always, every single reaction that will ever exist, where you have an exothermic reaction, and you have an increase in entropy, will always be spontaneous. Remember, spontaneity doesn't tell us how fast, but it does tell us that it will eventually happen. Okay? So that's really cool. If we know those two things, we know this reaction will happen, it will be spontaneous. Okay? What about if delta H is negative? So we have an exothermic reaction, but our delta S is negative. So we've decreased the entropy in our system, right? So we've got delta, remember we've got all this delta G equals delta H minus T delta S. So here I've got a negative value there, but I've got a negative value here. So at very, very low temperature, like T equals 0, my delta H is negative and my delta G is negative. At very, very large temperatures, I've got a minus a large number times a negative, minus minus gives me a positive, and I put a positive delta G. So these ones are generally only spontaneous at low temperatures. Now what does low mean? Low is relative. It means nothing all by itself. It just means there is a temperature, and below that temperature it's going to be spontaneous, and above that temperature it's going to be non-spontaneous. But we don't know what that temperature is unless we actually calculate it. But that's just what it means. Delta H is positive, and delta S is negative. Let's look at that one. So here we've got a negative here, we've got a positive here. Turns out no matter what I do, no matter what temperature, low temperature, high temperature, since I've got that negative T delta S, that's always going to be adding to it. right? And so a positive number plus a positive number is always going to be a positive number, and this reaction is never going to be spontaneous. You're never ever going to see an endothermic reaction that decreases entropy and can happen all by itself. Right? It can happen, but it's not without outside intervention. And we'll talk a little bit about how that happens later on. Okay, what about the last situation? Positive and positive. You can probably guess what that is. You can do the math and find out that those are spontaneous at large temperatures. Again, large is all relative. For some reactions, large might be 100. For some reactions, large might be 1,000 Kelvin. It just says, you know, as you get higher in temperature, the likelihood that you're going to be spontaneous increases as opposed to decreases. Okay. So notice a couple things. When they're opposite signs, plus and minus or minus and plus, they're set in stone, right? Either always or never. And when they're the same sign, you have to figure them out. So it's just a couple tricks to think about these things as you're going through. But it's all just related to the math of delta G equals delta H minus T delta S. If you know that equation, you can kind of figure out any of these things. But it is kind of a quick table to look at and think about. All right, that's the end of this section. The next thing we're going to do is continue our work with delta G and find if there's some easier ways of calculating it, which there are. Thanks so much for listening, and have a wonderful day.